this lecture, we will cover the number-based conversion. Even in the last lecture, also I have explained that how the numbers are like how the numbers are converted from one form of the number systems or say one form of the base to the decimal as well as another number system. Like suppose octal to decimal, we usually use to evaluate for the magnitude. Similarly, binary and hexadecimal. You always use decimal number system to evaluate the magnitude, and rest of the thing like decimal to octal you can convert, even though decimal to base 2 you can, like binary you can convert, and decimal to hexadecimal we can convert easily. Similarly, with the by the method of grouping, we just convert hexadecimal to octal and octal to hexadecimal by changing the grouping of the binary number system. We can convert the octal to hexadecimal and hexadecimal to octal. Similarly, by make a group of 3, we can convert octal or binary to octal, and if the group of 3 represented with the normal, like in the form of binary number system symbols, then we can directly just represent octal numbers into binary. Similarly, same we can apply for the hexadecimal also, but over here the group of bits when we try to convert from binary to hexadecimal is 4. Okay, so now I'll just explain you the same thing in detail in the next slides. Now you can see here the decimal to binary conversion. This is very first thing that we need to understand. This is the base of all the things. Like suppose we have a number 13 over here. So over here the base of the number is 30, and we tries to convert the decimal number, that is 13 that we understand, but binary number, that is the computer understand. So when we try to make explain something to the computer, that we have to talk in the computer's language. So the computer language is this 0101. Okay, so we first divide decimal number with the base. So whatever number is there that we want to convert from one form to another one, we can use the base as a like how, like in the form of decimal. Whenever we have a decimal to any form of conversion, the base is used to divide the number. If a decimal to octal is there, we will divide by 8. If decimal to hexadecimal is there, we will divide by 16. And if decimal to binary is there, we will divide by 2. So in this case, decimal to binary conversion is discussed over there. So 13 divided by 2, the quotient is 6 and remainder is 1. You have to use the remainder, not the quotient. Quotient will be used in the subsequent divisions. So like remainder will be used as a coefficient. Right? So 6 you will use for the subsequent divisions. So again, you have to go until you will not get the single digit or 0. Single, either 1 or 0. At last, that is not divisible. You have to reach up to the you have to do division up to that extent, or up to that point where you no further division can be possible. Okay, so like this 6. So 6 divided by 2, you will get the quotient 3, and remainder in this case 0. Okay, so 0 will be a second coefficient. Again, 3 is used for the next division. So 3 divided by 2, you will get 1 as a quotient and 1 as a remainder. Now 1 become the second coefficient. Okay, A2 coefficient. Now at last we have 1. So that 1 is not divisible by 2. So the quotient is 0 in this case because it's not divisible. Okay, and the one that you are using for the division, that becomes the remainder over here, and now it becomes the most significant bit. So now you have to form a number from most significant. This is the most significant bit of the generated binary for this number 30. So it's a 1, 1, 0, 1. So now in the form of binary, you can see over here also. This is the A3 is a MSB and A0 is a, it will become a LSB. Okay. So this, whatever number you get got first, that will become the LSB, and whatever number you got at last, that will become the MSB. Okay, so you will represent 13 as a 0, 1, 1, 0, 1. Okay, so this is the decimal to binary conversion. Similarly, decimal to binary conversion, it is represented in detail. This is the detailed discussion of the decimal to binary conversion. We're just moving toward the next conversion. Okay, fine. So again, in this case, the previous one is the integer. It's a decimal in the form of integer, and now decimal in the form of fraction. There is a bit difference. Okay, so over here base is same, but the number is 0.625. Number is 0.625. Now in the previous case, we are dividing the base. In this case, we are multiplying the base. If you remember in the previous case, okay, so over here we are dividing. Whenever we are trying to calculate the magnitude, we are dividing the base, but when we reverse the process, in this case we are converting binary to decimal, but in the reverse case, decimal to binary, you have to multiply. Over here, whatever is dividing, that will be multiplied, because in this case it is directly multiplied with the with the position, because of the position. Over here, because of the position, bit multi bit divide by the base. Okay, so in this case you can see that each number, when we tries to convert from decimal to binary with the fraction. Okay, so over here, whatever number you are getting, 0.0625, multiply by 2 first. So you will get the integer 1.25. You will get the number 1.25. Now you have to take the fraction for the subsequent multiplication, and whatever integer that you are getting, that will become the a minus 1 next to the mantis. There is a first coefficient. This will become your first coefficient. Okay, then 0.25 multiplied by 2, so that will give you 0.5. So the integer is 0 over here, so it will become a second coefficient. Then the last one is 0.5. So in this case, 0.5 multiplied by 2, 1.0. So the last coefficient, it will become 1. If we tries to multiply again, we just continue this thing again and again, then all are 0, 0, 0, so you will get 0, 0, 0. So there is no need to continue this thing after when you get the 0.0. Okay, so in this case we will start from the a minus 1, minus 2, minus 3. We will put 0.101. So that is the binary equivalent of 0.625 in a decimal. Okay, so this is the decimal fraction to binary conversion. Okay, so you can see over here, in the case of integer, numbers are taking from last to upside. In the case of fraction, numbers are taking from top to bottom. Okay, so this is the decimal to binary conversion in integer and fraction both. Okay, so the table where we can see the decimal to binary, all decimal to binary conversions are there. 1 1 2 1 0, 3 1 1, 4 1 double 0, 5 1 0 1, 6 1 double 1 0, 7 triple 1, 8. Now you can see over here up to 7 you can represent like this. From 8, 1 triple 0, 1 double 0. binary equivalent of decimal numbers from 1 to 30. Okay, so next is the decimal to octal conversion. So in the previous case, we have seen the all the binary 2 decimal, octal 2 decimal, and hexadecimal 2 decimal. So that is called the magnitude uh, calculation. How the magnitudes will be magnitude calculated, magnitudes are calculated. Now in this case, we have a decimal number. We try to calculate octal number, equivalent octal number. Now in this case, you can see that the number is given 175 with base 10. Now to calculate for the integer part, we have to divide. As you have seen in the previous case also, whenever we try to calculate for the integer, we usually divide 175 divided by 8, that will give you constant 21, and remainder is 7. So that will become the least coefficient. Okay, that is the A0, 7. Similarly, 21 divided by 8, so 2, remainder is 5, that will become the A1. And 2 divided by 8, that is not divisible, so quotient is 0, and remainder is 2. So that will become your most significant bit. So the final number that will be that is the that is equivalent of 175 into octal is 257. 257 is your equivalent number of 175 in decimal. Now similarly, when we have a number in fraction, so we have to again multiply, and we take integer as a coefficient, and remaining fraction that you are seeing on the screen, that is the uh, 0.5. So 0.5 will be used for the subsequent multiplication. Okay, so that will give you a minus 1 to a minus 2 4. So 0.3125 in decimal, that is the equivalent of 0.3125 in octal is 0.24. Okay, so this is the decimal to octal conversion. Similarly, we have a decimal to hexadecimal conversion. So in decimal to hexadecimal conversion, again same method you have to use, and we have to, whenever we are dealing with the integer number, we have to divide by 16. Okay, we have to divide by 16. 16 is the base, that's all. Okay, and we will get the number like 50. Okay, suppose we got the remainder 50, so we have to represent with the unique symbol, that is the F over here. Similarly 11, then we have to represent it with the B, and 7 is there, so 7 is not divisible, so final answer is a 7BF. We can represent 1983 in hexadecimal is 7BF. Similarly, we have to multiply, when we have a fraction number, we have to multiply with the base until we will not get the answer 0. Sometimes it may happen, it go into a recurring mode. It's like it will give you some number and you can represent with 0.9 dash 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 dashes. Okay, so that is also happen. So the final answer is over here is 0.9. Okay, this is decimal to hexadecimal conversion. Similarly, as we have discussed, we can also convert binary to octal. Okay, suppose a number is given that 10,110.01. So in this case, what we need to do, we have to start with the fraction. Okay, first we will go toward the left side. Okay, and we first try to create the group of 3. So in this case, group of 3 is 1 1 0. Next is a 0 1. Can't make group of 3, so we can put here 0. We can put here 0. Okay, so the equivalent according to this table. This is a table of octal to binary. You have to remember that this is the octal number system symbols, and this is the equivalent binary of the octal number. So for 0, we can represent it in the form of group of 3 0. when we have a symbol 1, we can represent in form of binary 0, 0, 1. Similarly, likewise, we can represent 7 as a 1, 1, 1. Okay. So, if we refer the table 110, so 110 can be represented as a symbol 6 in octal number system. Similarly, 010 represented as a 010 represented as a 2 in the octal number system. Similarly, over here, if we again move toward the right side from the Mantissa point, then we have 010. Okay, so that is also represented as a 2 in the octal number system. So this is binary to octal conversion. Binary to octal conversion. And the number 26.2 is the octal number or say octal equivalent of the binary number 10110.01. Okay, so this is binary to octal conversion. Now, binary to hexadecimal conversion. Over here, we have a group of 4. We are taking the same number, that is 1111000.01. Over here, we just start from the Mantissa point 0110. We make a group of 4. So according to the table, 0110, 0110, it's again 6 over here. Now, in this case, we have just a single number, single digit is there. We can, to form a group of 4, we can put 3 zeros before. Okay, then we can have a group of 3, a group of 4 digits. So 0, 0, 0, 1. So again, it's a 1. Now over here, 1, so from the Mantissa point, if we go toward the right side, so we have 0, 1 only. We can't form a group of 4, so we just put 2 more 0. 0, 1, 0, 0. So according to the case 0, 1, 0, 0. So that is 4. So the final number or say equivalent hexadecimal number of binary 10110.01 is 16.4. Okay, so this is the binary to hexadecimal conversion. Now, suppose you want to convert octal to hexadecimal conversion. So, whatever octal number is there, first we will convert into binary and then we can make the group of 4 and we can convert it in the form of hexadecimal. So, this is octal to binary and binary to hexadecimal. Similarly, if we have a number like this, we can first convert into the binary and then binary to octal. Okay. So, this is the number based conversion. This is called the number based conversion. Okay, so this is the